Hello, in this video we will discuss the concept of blackbody radiation. We will also discuss the problem of ultraviolet catastrophe that arises due to the limitations of classical mechanics, and in the following video back it up with some concrete mathematical reasoning. Firstly, let's see what a blackbody is. Definition of a blackbody. Right. So a blackbody is an idea of energy, no passing on of energy. So to define a blackbody is an ideal body which allows the whole of incident radiation to pass into itself without reflecting energy and absorbs within itself this whole incident radiation without passing on energy. So let's look at this in a diagrammatic perspective. So this is a sample black body with a small aperture with its outer surface is completely colored black and inner surfaces are silvered, that is, it acts like a mirror, right? Now this whole property is valid for radiation corresponding to all wavelengths lambda and is independent of angle of incidence, right? So if light enters here, it is reflected in all directions from this point everywhere. This property of black body to absorb all wavelength of light at any angle of incidence is something which is ideal and is something characteristic of a black body. Now, for example, if we consider this an ideal black body, you have light incident here. So light enters the aperture, gets reflected by the silvered mirror. It's reflected in all directions. Light just manages to be inside the cavity the entire time, right? Example of a black body material which we have in daily life and which was used in experiments extensively in the 19th century is something called pitch blende. Right. Now, mind you that a black body is only an ideal body and is only used as a yardstick, a standard with which the absorption of other bodies is compared, right? Now, this concept was introduced in 1860s by the German physicist Gustav Kirchhoff. And today it is called a black body because those bodies that absorb incident radiation, light, visible light, seems to be black to the human eye, right? So if I have a box or a body, and if I have visible light here, that is light which I can see, and the body absorbs all of that, then the body turns out to be it appears black. That is how the term black body came into being. The term is purely conventional and has historical roots, right? So one interesting question is, at a particular point, the temperature of this black body is in equilibrium with the surroundings. Otherwise, this will be violating the second law of thermodynamics, and it's all in a mess. So we'll talk about that sometime later, right? Now, one important point I wanted to make is anything can be a black body. There are always deviations from a black body. For example, our sun is a very good example for a black body, and it is not black. All black bodies are not black, right? So our sun is a black body. It absorbs a wide band of electromagnetic radiations. Now our sun appears yellow and sunlight at least bright white, as it represents the equilibrium light wavelength that the black body reflects. So at one point, the black body, for example, if this was our sun, it absorbs electromagnetic radiations of all wavelengths and only reflects light after it is in equilibrium with the surroundings. And this light turns out to be bright white in color, or sunlight. So in 1860s, 1859, 1860s, Kirchhoff also showed that the emitted light, the emitted radiations from a black body, or something called the emissivity of a body, to its absorptivity, that is the amount of light absorbed by a body. Now this ratio is, numerator we have the amount of light emitted by the body, which the body emits after it is in equilibrium, to the amount of light absorbed by a body. This is same for all bodies, at the same temperature. Mind you, when I talk about all bodies, I'm talking about black bodies. So for a black body, emissivity to absorptivity ratio is the same at the same temperature for any wavelength, for all wavelengths lambda. If you have a black body, if I have multiple black bodies like this, then the ratio of the light emitted by this black body when it is in equilibrium with its surroundings to the amount of light absorbed by this black body is the same for the entire sequence of black bodies at the same temperature. Now, Gustav did this experiment where he had a series of black bodies. He keeps a series of these black body shaped objects and at different temperatures, T1, T2, blah, 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 Tn. And you have light here, you have reflections, and you have some emissions, similarly everywhere. So you get a distribution of temperature. So you have a distribution of light radiated by these black bodies. And from this distribution, one can find out experimentally the power emitted by each black body. And as a form of normalization, you can get the power emitted per area, right? So when you plot the power emitted per area, okay, versus wavelength at different temperatures. So you pass light of one wavelength and you get light of different wavelength. When you plot this graph, you get the following distribution at different temperatures. So this is temperature T1, this is temperature T2, this is temperature T3. This was experimentally done, and you have T3, you have temperature T2, temperature T1, where the important relation is T3 was greater than T2, this was greater than T1. So in this set of black bodies, if I have a black body at temperature T1 and if I shine light of wavelength lambda, say a specific wavelength lambda, then the power emitted is this one as follows. Similarly, for all the set of wavelength, it has a one peak emissive power emitted, and this peak shifts towards a lower lambda as temperature increases. So as temperature increases, the peak emissive power per unit area increases with temperature, right? And at increased temperature, the wavelength decreases, right? So the general held concept that what produced these differences in maximum power emitted, scientists knew or physicists knew that it was something to do with atoms. So you have an atom molecule and you shine light of wavelength lambda and you get different light of energy E1 and you get energy E2. Now the only possible motion that could produce this change of energy was if the atom was perturbed, and this was explained in the form of a spring. So you can model the atom in the form of a spring, and the vibrations of the spring with some frequency mu, so the frequency of vibration of the spring, produced the change in energy. So energy E1 was used to vibrate the atom, and the remaining lost energy was E2. Now from Maxwell's theory, the possible frequencies in a frequency band d mu, the number of mu in the frequency d mu turns out to be this, right? So I'll attach a document which supplements this, where V turns out to be the volume of this cavity. Yep, where V is the volume of such a cavity. Right? Now measurements sample the energy of some wavelength interval using Maxwell-Boltzmann's work in statistical mechanics. If a particle is in an environment at temperature T, we're talking in Kelvin here, then the probability that the energy of the particle is between E, E plus dE was given by this. Probability the energy of the particle is between E and E plus dE was given as follows: AE power minus E by lambda kt by dE, where k is the infamous Boltzmann constant. Now, one important concept of probability is if P of E is given this, then integral P of E dE over the entire set of E's be equal to 1. This is nothing but normalization. Now when you do this integral, you get that A is equal to 1 by kt. You can look at the link for the integral below. And when you find the average energy, that is, try to solve the following problem: E into P of E dE, then this integral results in kt. Now, thus, given a number of oscillators or number of atoms in a black body as this, what is the average energy and the total energy? Now, this was the energy of one atom, right? Now, we have a series of atoms here. We try to find the energy of that. So, the energy of the system will be N of mu d mu, which is this. This turns out to be 8 pi V by C cubed kt and mu squared d mu per frequency. And when you plot this, when we try to plot, now notice that 8 pi V C cubed k and t are all constant. We're talking about one particular temperature. When you plot your energy versus your frequency, this can be called as k bar mu squared. Your energy of your system is a function of square, so which is like an x squared graph. And as you go to infinity, as mu becomes infinity, energy of the system goes to infinity. And this is a catastrophe. Now how can physically a system where the frequency of particles be infinite, and even if it's infinite, how can its energy go to infinity? This is where this is a limitation presented by classical mechanics, right? This is fine at the regime of lower frequencies, but blows up at higher frequencies. This is what we term as the ultraviolet catastrophe. Now later, Max Planck comes up with an ingenious guess of something which tries to solve this problem and then gives birth to the field of quantum mechanics. That's it for this video. Thank you.